on the top half of this page, we're going to look at capacitance and the permittivity constant. And then on the bottom half, I'm going to show you the different derivations that you'll be doing with the cylindrical, the spherical capacitor, and the isolated sphere. So we'll talk more about that in a moment. Well, first, the capacitance and the permittivity constant. This is really just a little bit of an aside for us, because we don't really need to delve into this right now, but we'll get back to it later in the course. So again, for completeness of your notes, and later when we do electromagnetic waves and talk about the importance of this permittivity constant epsilon naught, we'll recall that we've kind of seen this before, that there is some physical meaning buried in there. So where's the buried physical meaning? Well, we know that epsilon naught is 8.85 times 10 to the minus 12 coulombs squared, right, divided by Newton meters squared. Where C, of course, is not capacitance, that's our unit coulomb, so we have to be careful about that. Please make sure you get that in there into your notes. And if we look at the relationship between electric field and voltage over here, so I'm going to kind of bear with some of this. F equals QE, E equals then newtons divided by coulombs. Voltage is ed, electric field, times D, so we have Newton meters divided by coulombs. Well, we have Newton meters and coulombs up here, right? We have a Newton, we have a meter, and we have coulombs. So to go from here to here is to note that we are taking C divided by Newton meters on coulombs. There's your volt times meters. So that definitely works out. It's a little maybe not obvious at first. When we do that, so now we have our coulombs on the top, volts on the bottom. Well, we know capacitance is coulomb per volt. So to go from here to here, all we are noting is that we will have coulombs per volt, which is a farad, divided by volts meters, but volts on volts. So we lose the volts on volts, and a coulomb per volt is our farad. So farads per meter. Kind of cool. Here's our physical meaning now. So we have farads per meter. That means farads per meter of what? So capacitance per meter turns out of empty space. So it's kind of cool to think about the fact that even empty space, vacuum, nothing is there. Why should vacuum have any characteristic associated to it? But when in terms of how electric fields interact through regions of space, and we'll again see more about that later in the course, how it is that electric fields act in space, that this epsilon naught describes part of the properties for how electric fields act in space based on the capacitance per meter of the empty space. Now, you have 3 pages in our notes that you will be doing these derivations for yourself, but just to kind of get you started on each of the 3, your Gaussian surface for all of these derivations will go between the plates. So your Gaussian surface here will be a Gaussian cylinder between the positive and negative plate. For the spherical, we'll explain the capacitor part to you later, is a sphere around between the plates, so around the positive plate. Now, the isolated sphere, believe it or not, does have a capacitance associated to it. So even just a sphere by itself, a positively charged sphere, the negative plate in terms of the capacitance is assumed to occur at R equals infinity. So please put that in here. Then our Gaussian surface that we'll use will be anywhere between capital R and infinity, because that's our negative plate. So we'll again use a spherical surface anywhere between capital R and infinity. Now, we're going to prove this result. You're going to do your Gauss's law, plug it into the delta V equation, and then plug it into C equals Q on V, just like we did for the parallel plate capacitor. But when we do that, we'll see that for the isolated sphere, which is just like a ball of charge, has a capacitance of 4 pi epsilon naught R. So the capacitance increases directly with R. If you double R, you double the capacitance. Well, Q equals, as it shows here, Q equals CV. So now we know how charge will be shared based on having different size spheres come into contact with each other. When they come into contact, the thing you definitely need to focus on and to know is this bit here. When they touch, they will have the same voltage. So electrostatics, we won't have a voltage difference allowing for the movement of charge. It'll equilibrate, same voltage when they touch. But the charge on the smaller ball will be less than the charge on the bigger ball based on the capacitance value, the C2. And it's linearly proportional to R. So if the radius is half the radius of the larger ball, it'll have half the charge. So you have the derivations to practice on at the back of your notes here, pages to do the derivations for yourself, and you'll have videos to check your solutions.